Gauss's law, or Gauss's flux theorem, relates the distribution of electric charge to the resulting electric field. It tells us that the net outward electric flux through any closed surface S, so this flux will be equal to the net charge inside S divided by epsilon 0. So this flux is only determined by the charges that can be present inside this closed surface. In practice, we often use this to indirectly compute the electric field when the inside charge is easy to know. For example, we can compute the field created by an infinite line of charge, and instead of doing it with complicated integrals for p going from minus infinity to plus infinity, we would simply benefit from symmetries to reduce calculus and simply use the flux theorem to compute E. How does it work? When we know symmetries of charge, with Curie symmetry principle, we know also about symmetries of the field. For example, we can know that the field depends only on one single variable. Even more, we can know that it is, for example, going always through x direction, or it can depend only from r and follow only z direction, etc., depending on the symmetry. When we know these symmetries, we choose an appropriate Gauss surface, which follows the symmetries of the field, and of course also the symmetries of the charge, as these are influencing the second. In the case of an infinite line, as the problem has a cylindric symmetry, an ideal Gauss surface would be a cylinder around the axis, because it offers the advantage of having a normal vector of the surface, which is following the cylindric symmetry and following ER, and another surface where M is simply orthogonal to ER. So if the symmetries tells us that the field is following the cylindric representation ER vector, we just know that we all have to compute the flux in this part of the surface, and as the field doesn't depend on theta or z, this integral would be very easy to compute, as we would be just computing the integral of a constant around something depending from theta and z, which is this surface, and as the surface vector is driven by n and E driven by ER, which is nothing else than n, this would simply look like ER times the whole surface, and as S is simply equal to 2 pi RH, this would be easy to compute. This is depending only on R, and the charge inside S is only equal to this line in red, which can be computed if we know the charge density. There would be a video on computing the field created by an infinite line, but what I want to highlight here is the choice of an appropriate Gauss surface that often has two faces, a face orthogonal to the field and a face which is parallel to the field. So first symmetries, then appropriate Gauss surface, then an easy computation, often integrating a constant instead of doing this complicated integral computations.